Hello, everybody. I'm Anniina and Jouni is here with me. I am a meteorologist here in FMI. I work at Weather Services and Jouni is PhD at University of Helsinki. So let's start with today's topic. First, I want to know where you guys from. So I would like you to mark on the map where you are from and what do you do? Nice. There's a lot of us here. A lot of you are forecasters and few other. What do you mean by other? Well, let's start with today's topic. I'm going to have a brief overview about the weather here in Europe. I'm not going to concentrate on any specific phenomena. And Jouni will talk about the heat wave, not only in Finland, but in Europe. So I would like you to draw jet streaks on this water vapor map with using tools here in FX. Yeah, perfect. Here's what ECMWS thinks about jet streaks. So this view is from yesterday, 6 UTC. So as you can see, all those dark areas are the jet streaks, and those yellow lines are ECMWS forecast. They are not really aligned with the satellite image, but you can see what's really happening. There is some dynamically active areas and ongoing cyclokinesis. So there are heavy thunderstorms in Croatia, and there is low pressure here in northern Atlantic that moves towards the northeast. And during this summer, all these jet streaks were moving here in very north, and we had really warm air in Finland or all in Northern Europe. But now we are seeing some signs of autumn because of all these jet streaks are moving towards south and we are getting colder air. Here is air mass picture from yesterday. You can see warm air masses with the greenish color, cold air masses with the bluish, purplish colors here and here, and some ongoing cyclokinesis we were talking about earlier. This image is from yesterday, and this is from today morning, so you can see the cyclokinesis going on here in the northern Atlantic. This picture is ECMWS 850 hectopascal temperature, and you can see there is a lot of warm air masses covering almost entire Europe, but you can see there is colder air mass moving towards southern parts. There is one weird coloring in this image. There is bluish color over Russia, even though the air mass is really warm. And all those bluish colors are telling that the air mass is cold. But we saw in this picture that air mass is really warm in Russia. But the coloring in this air mass image is wrong. The reason why the color is blue over Russia is the effect called limb cooling effect. The ozone absorption increases with increasing satellite viewing angles. So that's why the color is misleading. So it should be greenish, but because of the satellite image angle moves, the color is bluish. Here are some nice to know stuff. Can you spot where is the smoke trails from Northern America's forest fires? I'd like you to draw if you can spot it. Yeah, perfect. But do you know why it's pink? We asked our research why it's pink. So the stream is shown only in this channel, the demicrostatistical RGB channel, during the sunrise. And normally the pink color indicates snow and ice on the ground in this RGB channel. But the color pink is due to because the backscattering from the particles during the sunrise. So you can see all those channels in here. You can see green, blue, and red. And on the red channel, you can see the smoke, but on the green and blue channels, you cannot see the smoke. So the pink color is because of this visible channel. And then we had some snow in the middle of the summer. Can you mark where you can see the snow? Yeah. It snowed in the Austria, so cyan color shows the snow in the day, natural colors RGB channel. So the really bright blue colors are showing the cold near the ground or the high clouds. And before Jouni starts, I would like you to mark your highest temperatures you measured during this summer in your country and in which city on these tables, if you know this far, yeah. So in Finland we had the almost 34 temperature Celsius in Vaasa this year, this summer. Well, I think the summer is almost ending here in Finland, but you guys are enjoying still summer. So if you know your highest temperatures in your country, I would like you to mark it here. The highest temperature that has been measured here in Finland is 37.2 degrees of Celsius. It was in the summer 2010. Yeah, so it's not much. It's not much comparing to Germany and other countries. Who wrote the one wherever I went is too high? Because that's funny. Yeah. Thank you for your attention. Now it's Jouni's turn. So let's change the slide to Jouni. There you go.
Okay, let's also change the person. So I'm Jouni Räisänen from the University of Helsinki, and well, I thought to give you some information about the general relationship between climate change and warm extremes. So Basically, I'll discuss here two separate issues. Most of this time I will focus on some basic statistics, and slightly simplifying, I'm saying that increases in mean temperature lead almost by definition to an increase in warm extremes, regardless of the details of the weather systems. Then there is another hotly debated but much more difficult issue, is this ongoing Arctic amplification in the warming having an impact on the nature of mid-latitude weather systems and, for example, on the occurrence of long heat waves. So, but I will start from this first one, and this is a very well-known diagram published by the IPCC already 17 years ago. And what this diagram shows is the distribution of temperatures in two climates. The curve on the left, it shows a baseline climate, and the curve on the right shows the distribution in a warmer future climate, assuming that there is no change in variability. And it's quite obvious that when we have this increase in mean temperature, it leads to a decrease in the frequency of cold extremes, but quite a pronounced increase in the frequency of hot extremes. So, of course, now in reality, the variability might not be constant. It might either increase or decrease depending on the situation. For example, if an increase in mean temperature is combined with increased variability, so of course the increase in the warm extremes becomes even larger. Well, from a theoretical point of view, it has actually been suggested already in the 1990s that changes in extreme events in a climate are more affected by changes in variability than changes in the mean values. However, this actually only holds when the changes in variability are comparable in magnitude to the change in mean value. And in fact, when we look at climate model simulations for anthropogenic climate change, they very strongly suggest that, as a rule, in most situations, the changes in temperature extremes will be much more affected by the change in mean temperature than by changes in variability. So let's take one real-world example. This summer was warm in many parts of Europe. In Finland, particularly July was very warm, and the largest warm anomalies in this case were observed in the north of the country, in Lapland. So I take Sodankylä from central Finnish Lapland as an example. Observations in Sodankylä go back to the year 1908, and during this period of observations, excluding this year, the average July mean temperature at this location was 40.6 degrees. The highest value before this year was in 1925, 80.5 degrees. However, in this July, the mean was plus 20.1. So the previous record was exceeded by 1.6 degrees centigrade. And although this temperature is not so extreme, would not be that extreme in southern or central Europe, it's really an extreme of extremes in Finnish Lapland. So now it's interesting to ask, what is actually the probability of exceeding 20 degrees centigrade in July in Sodankylä? Now, when we have this observed time series, it's of course possible to estimate an analytical distribution, and one gets something like this. So here is the probability of distribution of temperature in July in Sodankylä based on this 110 years of past observations. So now to estimate the probability that the temperature exceeds some threshold value, for example 20 degrees centigrade, we need to calculate the area that falls below this probability curve and to the right of this threshold temperature. So in this case, this blue area is actually quite small. It corresponds to a probability of the order of 0.2%, which is of course a somewhat uncertain value because we need to extrapolate a lot beyond the actual observations. So this analysis suggests that based just on these observations for the past 110 years, the mean temperature that was observed in this July should only occur on the average once in 500 years. However, there is the problem that most of these observations in the time series are actually from a period when the climate was still both regionally and globally colder than it's today. So these observations are not really representative of the present day conditions. So to estimate this probability and the actual present day climate in general, we must take into account climate change. And there are several ways in which this could be done. I'm using here a method that was introduced by myself and Leena Ruokolainen in a paper in Climate Dynamics 11 years ago. And the basic idea here is that I'm combining information from observations and model simulations. So I'm using the observed time series of the global mean temperature, which has a pretty good signal to noise ratio between climate change and variability. And I'm combining this with model simulations of the regional patterns of temperature change. That is the simulated change in local mean temperature, normalized by this global mean warming, and on the change in variability, normalized by the global warming. And using all these sources of information, we get kind of synthetic time series that bring the observed temperatures to the present day climate conditions, or you can also apply this to the future climate. So here is what model simulations are saying. So this is based on the semi-5 ensemble of global climate models and taking the average of all model results. They are suggesting that in July in Finnish Lapland, on the average, the mean temperature should increase by about 1.2 degrees for each 1 degree of global warming. On the other hand, the standard deviation doesn't seem to be changing that much. Or on average, there is 1% increase in standard deviation for each 1 degree of warming. It is practically negligible. So this is what I already showed you, the observed temperatures in Sodankylä in July. Now, combining this observation of the global warming and the climate model results, we get this red time series, which gives an estimate for the temperatures that would have been observed otherwise in similar weather conditions, assuming that the global mean temperature had always been at its current level. So in the end of this time series, the red and the blue lines are the same. However, the difference increases toward the beginning when the global mean temperature was still substantially lower than it's today. So now we can repeat this exercise of estimating the probabilities. So this blue line was based directly on the observations. And when we take this red line instead of the blue line, we of course get a distribution that has shifted to the right. So the climate has become warmer. And in fact, this shift is not that large in this case, but nevertheless, when we look at the probability of actually exceeding 20 degrees centigrade, it has increased in relative terms quite substantially. So this 0.2% probability has increased to 0.8%. So, of course, there are several sources of error in this calculation, but if we assume that these numbers are correct, they suggest that July as warm or warmer than observed this year in Sodankylä is actually now about 4 times less unusual than would be inferred directly from these past observations. So in this sense, one can claim that there is a 75% probability that the warm July would not have occurred without climate change. On the other hand, one can also look at this from another point of view. Even if although we have had this warming climate, the mean temperature in this July was so high that not much of this warm anomaly actually can be explained by climate change. If we take this red line that is supposed to represent the present climate conditions, the mean value is about 15.4 degrees centigrade. It is still 4.7 degrees colder. So in this sense, it's quite clear that most of this very large warm anomaly in this summer was caused by natural variability, and the role of climate change was only to make this extreme warmth even more extreme. So then we have the question about what is going to happen in the future. The diagram here on the left shows time series of the global mean temperature in this global climate model simulations from the SEMIFY project. And we have these 4 different RCP scenarios with different levels of greenhouse gas emissions. We have this RCP 2.6 scenario where the emissions decrease quite rapidly. In this case, the warming would stabilize to around 1 degree centigrade, about the level of the late 20th century. And other extreme, there is this RCP 8.5 scenario with very large greenhouse gas emissions and a very large warming, or about 4 degrees centigrade in the global mean by the end of this century. And of course, in addition to this, these temperature changes also vary between these individual climate models. So we can be pretty confident that the global warming will continue, although the magnitude of the warming in the long term is still quite uncertain. But in any case, let us assume that these model simulations are right on the average. I'll come back to these probability distributions of July mean temperature in Sodankylä and take 3 examples of how this distribution might change based on the model simulations. So I consider this moderate, so-called RCP 4.5 scenario, with the second lowest here for the middle of this century, and for here 2090. And the last example is for the RCP 8.5 scenario, with much larger emissions of greenhouse gases in the year 2090. So to again repeat what I already showed to you. So here we had these first 2 distributions, one directly from the observations, and the second one as estimated for the present day climate. Now if we go to the year 2050 and take this RCP 4.5 scenario, we again go towards higher temperatures, and this of course leads to an increase in temperatures exceeding 20 degrees centigrade. Still, the probability is only of the order 2.5%, but nevertheless, it's 3 times more common than in the present climate. Then if we proceed to the year 2090, under the same scenario, again we have warmer temperatures on the average and about 8% probability of exceeding 20 degrees centigrade. And finally, if we assume that things go badly in the world and this RCP 8.5 scenario is realized instead of this more moderate scenario, actually typically in about 1 year out of 4 we can expect to have temperatures that are similar or warmer than those observed in this year. So here the generic message is that the frequency of warm extremes increases very rapidly and non-linearly in a warming climate. Nevertheless, the answer to the question that is quite often posed by media, was this and that extreme event associated with climate change, depends on the formulation of the question. So first of all, for any large warm extreme, most of the temperature anomaly, as measured in degrees centigrade, still must be due to natural variability. But despite this, the probability of reaching very high, that is record or near record level temperatures, has already become much larger due to climate change and will continue to increase in the future. So this example was for Finnish Lapland, but of course these strong heat waves also occur elsewhere in Europe. And in fact, when we look at these model simulations of greenhouse gas induced climate change, we can expect that this relative increase in the frequency of heat waves will be even larger, because the mean temperature probably will increase more in southern Europe than in northern Europe in summer. And in addition to this, the interannual variability of temperatures also tends to be somewhat smaller in the south than in the north. So the signal to noise ratio between the warming and the variability is larger in the south than in the north. So this was all relatively straightforward. What is much less straightforward is this possible relationship between Arctic amplification and mid-latitude summer weather conditions. This is a hot topic. It has been discussed in a large number of present papers, which present some different ideas of this. But in any case, the basic mechanism is that if we have a maximum in the warming in the Arctic or in northern Eurasia and northern North America, this will tend to reduce the temperature gradient in the mid-latitudes, which tends to make the baroclinic storm tracks weaker. It may also shift the jet streams depending on the details of this warming pattern, and it might favor stronger, persistent or quasi-stationary waves. And all these mechanisms have speculated to lead to more persistent mid-latitude weather anomalies, that is smaller high-frequency variability, but possibly stronger low-frequency variability. And if, in fact, this low-frequency variability increases, this might increase the risk of long heat waves, in addition to the effect that we get directly from the global warming. So, as said, this is a speculative and somewhat messy issue, but what is currently known is that observations seem to give some evidence that at least some of these different mechanisms are working in the atmosphere. And also there is some suggestive evidence, although this is not yet very strong compared with the natural variability, that the persistence of mid-latitude summer temperatures has actually increased in the last few decades. But quantitative understanding of these issues is still very limited. In any case, I would like to advertise that just last week there was a review article in Nature Communications about these different mechanisms that gives a good overview of what is known about this topic currently. So, to briefly conclude, global warming leads to a large increase in the frequency of warm summer extremes. This increase is mostly explained statistically by the increase in mean temperature rather than increased variability, although variability might indeed increase in some areas. And finally, these dynamical mechanisms that are associated with the Arctic amplification of warming might enhance the increase in heat waves by favoring larger low-frequency variability. But this is still somewhat speculative, and my impression is that it's still likely a secondary effect compared with the increase in heat waves that simply results from this increase in average temperatures. So, this was everything from my side.